Hi, everyone, and welcome to the last of our three short talks. I don't know how the time flies in this event, so it's a pleasure to have Julien Cameron-Lemire from Nord Quantique here today. And we are going back to Harvard now and to Canada. So, looking forward to your talk, Julien.
Thank you, Araceli. So very happy to be here. Very happy also to be a silver sponsor of this event. I think it's very fun to have all of you people joining and seeing all the careers that are there open for you. So yeah, today I'll be speaking a little bit about what we do at Nord Quantique in terms of developing hardware but tailored for error correcting quantum processors. So I'll tell you a little bit more what we do into this field. And also tell you a bit about Nord Quantique itself, so where we come from and where we are going, and also the career opportunity, of course, that are currently open inside our company. Okay, so let's start with this. And before I really start talking about what we do, just want to take a step back and talk a little bit about the big challenge in the field of quantum computing right now and what we are trying to solve with the company. So as you know, quantum computing is something that is happening. So everyone can now connect to a web platform, design an algorithm, and send it to one of the distributor quantum computing of quantum computers, and have answer from these systems. So this is great. The field is progressing quite rapidly, but one major problem with existing quantum computers is actually the fact that the current hardware still makes a lot of error. So if you look at the qubit inside hardware of these platforms right now, the qubits makes about an error every 1,000 operations, which limits either the size of the chip that we can build with quantum computers, or conversely, the size of the algorithm you can run. And of course, this limits the commercial impact of these machines at the moment. This is really a big challenge that needs to be solved in order for the field to go forward. Of course, this is not a challenge without a solution, though. And the solution is called quantum error correction. And in this field, what people are envisioning to be doing is use many of the physical resources onto the quantum computing chips, and use this ensemble of physical resources, so the physical qubits, in order to make a single logical qubit that will carry the calculation. So even though this is a proven technique, so you can actually correct error using this method, the problem is that you suffer from a large overhead in terms of the number of physical resources you will need to put onto a chip for this technique to be successful. And we're talking about 1,000 to 10,000 physical qubits for every logical qubit that is actually doing the calculation. And to us at Nord Quantique, this is really an indication that we need better hardware. We need to find ways to reduce this overhead so that we can, in the end, really build a big quantum computing machine and have impact with this technology. And our approach to this is what we call an hardware efficient approach. And what we're trying to do is migrate the error correction layer all the way down to single qubits. And the way we do this is with a technology that we call bosonic codes. And these bosonic codes are simply microwave photons that are hosted into a superconducting qubit, superconducting architecture. So in our case, it's superconducting resonators. And what we can do with these resonators is have a bunch of photons inside of them and leverage the redundancy that is now intrinsic to this single resonator in order to make qubit out of them and correct and detect error inside single qubits. And these are just examples of the types of qubit that we are able to do with our quantum hardware. And you can see from this fingerprint, the repeated pattern is kind of the redundancy that we are leveraging to make error correction with single qubits. So the way these qubits are done is of course very different from more traditional two-level system qubit, which means that the roadmap toward quantum computation is also very different. So as I was mentioning earlier, if you have a two-level system type of qubit and you're trying to build a chip with a redundancy, what you need to be doing is some sort of a brute force approach where you pack a lot of physical resources onto your chip in order to reach this realm of fault tolerance, and where we think quantum computing will have impact in the future. In our case, with bosonic codes, what we're trying to do is really migrate the complexity of building a big chip into the complexity of controlling very well fewer physical system and doing error correction on single qubits. And this is where we are right now in our roadmap, trying to decrease the error rate by error correction on single and in few qubit type of chips. And in the end, the advantage of doing this is, yes, you save a lot of resources in the end. So for a given problems, you would need fewer resources for bosonic codes to be solving this. Or conversely, this also means for similar type, for similar size of chip, you're able to solve larger problems and also have more commercial impact with these machines. So this is really where we are going. And our mission with this is exactly this. So what we're trying to do is materialize the error correcting quantum computing by embedding this error correction layer at the very fundamental level of our chips. And we're trying to make every qubit worth as much as possible so that we save the big overhead when scaling. And we believe that this is what will lead us to compress time to scaling and realize fault-tolerant quantum computing. So this is really about our technology, and I will be happy to answer more questions about this at the booth if you have some. But now I'll switch gear a little bit and talk about the company where we are located and also what we are looking for right now in terms of talent and what are the job opportunity inside the company. So Nord Quantique, so we're located in the really beautiful region of Eastern Township in Quebec. So just the region itself is something I enjoy a lot myself being there. So it's a great place for outdoor. A lot of outdoor activity can be done, as we can see from this slide. But it's also a place where it's really well versed into the art of quantum and the art of technology development. So the city in which we are evolving is called Sherbrooke, and there's actually one of the three main quantum hubs across Canada, which is now located in this community. And the Sherbrooke Quantum Hub is actually growing, both in terms of scientific impact related to quantum technology, but also in terms of commercial development. And there's a lot of news that are coming from Sherbrooke in terms of growing the commercial ecosystem related to the quantum technology. So a very exciting place to be doing quantum, and this is why we are building our quantum computer there. And also as a startup, and especially as an early stage startup, so we have been created only in 2020, so it's been 2 years that we've been doing quantum computers. It's important to have access to ecosystem. And for us, this ecosystem is really located into this Sherbrooke Quantum Hub. So we have access to very different types of infrastructure, which goes all the way down from quantum science and to micro and nano fabrication, and even at an industrial scale. So on the left side, what you see is the Institut Quantique. This is the Excellent Science Research Center that is in Sherbrooke. This center is very interesting also because it's open for business, and startup like us can evolve within this infrastructure and have access to fridges, for instance, to do our quantum computer characterization. As a hardware company, we also build our quantum hardware. And right now we're doing this in a prototyping nano and micro fabrication facility. So this is a world-class clean room where we can fabricate our chip. This is called 3IT. And it allows us to quickly design, fabricate, and build new processes for our chips. And of course, in the future, we need to go at an industrial scale, both in terms of reliability of our fabrication process, but also in terms of the size of the chip that we will need to fabricate. And this is done with a partner institution which is close to Sherbrooke. It's in Vermont. It's located in the Northeast Microelectronic Corridor. It's a industrial fabrication type of facility, but where you can also prototype. And this is really unique to the Sherbrooke ecosystem. And as I was mentioning about bosonic codes earlier, one of the challenges is really to understand the physics and understand the science that is behind it, so that we can do error correction on single qubit. And this is really a challenging thing. And because of this, we're also backed by pioneers in the field. So both Alexandre, who is a co-founder of Nord Quantique and has been really involved in the company since the beginning, and also Professor Michel Devoret, who's now advising us also on the roadmap. And these two people are pioneers of the field of superconducting circuits, are pioneer of the field of bosonic codes. It's really helpful to have such a world-class talent getting involved with the company. And of course, so we're routed into science, but really what we are developing is we are trying to deliver, and not only trying, but also succeeding in delivering a technology. And this is why we've been able to secure, actually last month, so it's been announced that we've secured our seed stage funding, which is $9.5 million, so that we just received from 3 VC firms, so all specialized in quantum computing technology and quantum at large. So there's BDC from Canada, Quantination from France, so it's France-based VC, and also Real Venture from Montreal. And of course, with all this money, what we're intending to do now is scale the technology, but also scale the team. And I'll be talking a little bit about what sort of roles are now open inside our company. So really, as I've mentioned in the very, very beginning, so we are a quantum hardware company. We're really focused on building our bosonic codes hardware. And for us, this boils down into 3 different sectors into the company. So first, there's the quantum hardware, where we actually build the chips, assemble the chips, and also like characterize, understand what's happening in terms of physics, and trying to understand how to improve the hardware, really from a more experimental type of point of view. Of course, it's important to be able to design and simulate our system. So this is our simulation and theory group. This is where we also build control sequences for our hardware and improve on more on the error correction side of things there. And at last, so there's the nanofabrication sector. So I've mentioned that we are fabricating our chip, and this is a growing activity right now inside the company. So we'd like to have some people in this. So if you go on LinkedIn, you'll see that we have many positions across all these 3 sectors. So right now there's 8 positions available. I just want you to know that there will be more positions coming. So we are looking to scale the team up to 27 people in the next 18 months. So if you're interested about what we are doing, but not your role fitting exactly for you, go also to our webpage where we have an application form that you can solve, and you can tell us what your interests are in. So with this, thank you very much for your attention. I hope you can come and meet us at the booth. So we're 3 people ready to answer your question today, and also check our career opportunity on our website and on LinkedIn. So thank you very much, and have a good day, everyone.
Thanks very much, Julien. A very nice overview of the company. So there are some questions. Somebody asked, what is a bosonic code?
Yeah. So bosonic, so there's a word inside bosonic, which is boson. So what we're using is boson to make qubit out of them. So just as a comparison, so usually qubits are made of 2-level types of systems. So you have a 0, a logical 0, logical 1. And this is what you're working with. What we're using is a lot of photons, and what we are using is microwave photons. And we're trying to leverage the intrinsic redundancy of a large number of photons to create states that are actually qubits. And the thing is, because there's an intrinsic redundancy, we can do much more things with these qubits than what you could do with the 2-level system. And this is where we can do error correction with these systems.
Very interesting. Would you say that the company is solely a hardware company, or are there also possible software opportunities? I think you mentioned a little bit about that.
So at the moment, we're very focused on hardware. This is something that will change in the future. We are looking for software people. And right now, so the software that we're looking for is mostly related to the hardware. So it's more like firmware or these types of software that we're looking. But the application side of things will come at a later stage for the company.
Great. Junaid said, are you using silicon microresonator-based architectures?
We are using silicon chips, and for the resonator architecture, this is not something we are disclosing at the moment.
And I like this question from Rishi. What are the key concepts that one has to be familiar with to be able to work on error correcting codes?
That's a good question. I think it's on many things. So on the hardware perspective, it's really understanding where the error comes from. So understanding hardware and trying to build codes that are resilient against this error. So this is why like bosonic codes, the fields and how you do error correction in these codes is really emerging. So we know where the errors are mostly coming from in this type of hardware, and where the codes are designed in order to be doing this. So this is from a hardware perspective. And I would say from a more architecture type of things, I think there's many things. So what are you exactly trying to do? So is making a lot of qubits interacting together. So this is again understanding the physical system, be able to modelize it, model the error where they're coming from, and build codes that are good against these types of error. So it's really about understanding the system and design a way to simulate it efficiently, I would say.
Great. Okay, I think we stop there, and I think you're gonna be at the booth, right? So people can
Exactly.
join you.
So we have 3 people at the booth all the afternoon. So feel free to come and ask questions there.
Perfect. So thanks a lot again, Julian. And I will go now to the last talk that is gonna be me. But thanks a lot. I hope that you talk to a lot of people, interested people in Nord Quantique at the booth. And see you soon.
Thank you very much. Thank you for the event as well.
Thank you.